Hey everybody, I'm so excited to finally talk to you guys at the RSA 2021 virtual conference about my presentation, Windows Kernel Patch Protections, Achilles Heel, PatchGuard. My name is Arusha Gramper, and let's get started right now. So let's start with a little bit about me. I'm a high school senior at Amador Valley High School in Pleasanton, California. I'm a self-taught programmer, and I love working with the Windows operating system and all sorts of programming, such as the kernel, internals, other technologies such as RPC, COM, DCOM, etc. And I also have a few privilege escalation projects, which you can find on my GitHub page, and they work with code integrity systems of the operating system. However, that's enough about me. Let's get started right now. All right, so what's the agenda for our presentation? We're going to be talking about Windows kernel patch protections, or internally it's called PatchGuard. And we'll just go over a few objectives about why you would be attacking PatchGuard in 2021. And then we'll go over an intro to the kernel patch protection engine. We will go over and go through its response analysis. And after that, we'll have the bulk of the presentation, which is our attack walkthrough. After our attack walkthrough, we will have a short demo, and then I'll go over some problems and improvements that's with my attack right here. In the end, we'll talk about the mitigations and next steps for commercial, enterprise, and even home users, anybody who uses Microsoft products and Windows. And at the end, we will finally answer some questions. And if you guys do have questions along the way, feel free to just ask them in the Q&A, as you can ask them at any time. All right, so let's get started. So the objectives, why even bother with something like kernel patch protection in 2021? Well, the kernel is the heart of the operating system, and it encompasses everything. It runs at ring 0. It has the maximum privilege that you can do on the has a maximum privilege of anything you can do on your computer. And if you're able to compromise the kernel, you can bypass most of the standard security features in Windows. Now, it's important to remember that it isn't just Windows. Every operating system has a kernel because everything you do happens at the kernel. Now, why should we protect the kernel? Well, if your kernel is compromised, you can spy on data, requests, you get complete access to your hardware, and obviously that's not a good thing that should happen. So what even is kernel patch protection anyways? Well, it's a system that was designed to detect and respond to unauthorized kernel code modifications. Microsoft introduced it back in 2005 with the introduction of Windows XP on 64-bit editions with Server Pack 1. Now, patching the kernel, like I said, are just modifications, and it's never been supported by Microsoft. However, this system was introduced to detect those modifications and bring the system down in case one is detected to prevent further security compromise. It's like a bank alarm. It does not stop the actual bank robbery from happening, but it goes off when one is detected. And PatchGuard simply follows this cycle where it initializes, sleeps, it does a check, and then it takes a response action if necessary. All right, so what exactly does kernel patch protection check in the first place? Well, of course, it's going to check itself, and it checks the kernel and its associated data structures if they have been tampered or modified in any way. Now, what are those data structures? It is pretty simple. They just check 3 main categories: the generic data regions, CPU data structures, and objects and object types. Now, I won't list them all out as they're on screen, but these are core data structures used by the operating system almost every second during uptime. But however, kernel patch protection does not prevent other modules from being modified, except a few, such as the Win32K family series of drivers, which provide your user interface GUI functionality for the operating system, and the code integrity module ci.dll. And there's probably some others which I haven't figured out yet, but there are a few exempt modules. All right, so let's dig into the response analysis of kernel patch protection. We know what it is and we know what it checks, but what actually happens when something is detected? Well, what can you do when something is detected? It's not like you can go back and fix it because you don't know how it was modified. So the only logical thing that will happen is bringing the system down. There are 2 main stages when you crash the system. You will prepare for a system crash and then actually crash the system. Now, how does this work? Well, kernel patch protection will first capture some information about the corruption, and then it'll rewrite the call stack. And after it rewrites the call stack, it'll rewrite some save routines and then destroy the call stack in the end. Now, what does that do? Well, I'll explain that later, but we first need to understand the actual bug check process. And what is that? That's basically what the function KE-bugcheck as it is does. It brings down the system and causes a BSOD. Now, what are these saved critical routines? They are basically routines that are important in the bug check process. Routines, functions, they're interchangeable. Some of these are listed on the screen, and there are probably many, many more that are also critical, but I'm not just going to list them. And one of the pictures there is an example of a destroyed call stack from PatchGuard. As you can see, the first caller in the list is KE-bugcheck-X. We have no idea what was called before it. The classic security through obscurity model is used here because you don't want to know what caused the crash in the first place. All right, so now that we know what happens before a crash is issued, how do we need to understand what happens when the system is brought down. So like I said, PatchGuard will eventually call KE-bugcheck-X when a crash is detected. Now, what does that do? All it does is collect the CPU context and sets the current IRQL to dispatch level. After that, it simply increments the global variable KI hardware trigger, and that is shown in the assembly on the right. It is the first picture. And as you can see, it calls RTL capture context to store the current processor context in the kernel processor control block, which is a special control block used per CPU on a per CPU basis. And after that, it does some modifications on RTL capture context, so it does not represent the context of KE-bugcheck itself, and it represents the context of the caller. After doing that, you can see it simply increments KI hardware trigger with a lock prefix because it's an atomic operation. And after that, it will simply call KE-bugcheck2. Now, KE-bugcheck2 is where everything actually happens. You're using a computer, everyone knows what a BSOD is, blue screens, millions of people have heard of them. Where does that actually happen? That's where this happens. What it does is it spends most of its time preparing information, and it'll eventually write a crash dump, which is what you see when it says collecting error information, and it will freeze execution on other CPUs because the only sequence of execution that we want is going to be on the current CPU. After that, it will simply display the blue screen we all know and love, which is basically the function KI display blue screen. And in the end, it will reboot or break into the kernel debugger. All right, so now that we know what actually happens during the bug check process, such as if it will break into kernel debugger or not, it will just reboot, what information is collected, we can start to go over some flaws. Now, there is a number of flaws, but the biggest one, which you guys can probably tell, is that this all happens in ring 0 memory space. So everything happens in the same memory space. PatchGuard, kernel, other drivers, they are all in the same memory space. So without even needing to design and formulate an attack, you can already tell if something is in the same memory space with the same permissions, the same everything, it is possible theoretically to circumvent any security product that runs in that same memory space because there is no physical hardware bound isolation between the two, like if you're running in ring 1 or ring 2 on user mode, which is ring 3. The second major flaw that we have are missing protections. Now, PatchGuard, of course, is being used on every single Windows operating system, right? That goes for phone, mobile, server, Xbox, almost everything that runs the NT kernel. So of course, you are going to have some things that are not protected, but however, certain things should be protected because they are critical to system security, such as the .data section of the kernel is not protected. When you can do things like modified tables, global variables, and other things in the .data section, since it's not protected by .text or .idata or .edata. The other thing that's not protected is padding. The padding, if you're familiar with padding, is just a block of zeros in one of these sections. But why are they important? Well, that's because PatchGuard has a way of detecting callbacks that are not registered within drivers. If you manually map drivers where they aren't supposed to be, normally you would create a callback into your driver which is not in the loaded module list. However, since padding is not protected in PatchGuard, you can simply insert your own jumps into the padding, and just like that, you got around one of PatchGuard's detection mechanisms. So padding should be protected because it completely allows you to use callbacks that aren't even in the loaded module list. And the biggest problem with this response are the missing saved routines. Now, these saved routines are exploitable, and it's what makes this attack possible. However, like I said, not every single saved routine needs to be saved because some of them are inlined or are used so many times you probably won't have to rewrite them. However, some routines, such as the ones I'll talk about, are necessary to be saved in the kernel because these routines can be used to snatch execution and sabotage the PatchGuard response process. So what exactly are these routines? Well, there is one exploitable unprotected routine called memset. Memset, you're probably thinking memset, oh, come on, that's like what every C programmer learned when they just started. Well, yeah, that's what this attack is actually based on, memset. And you can see this attack is very simple. All we'll do is we will stop the PatchGuard response by calling memset, or when memset is called, all we'll do is check if the current caller is KEBugcheck2, which means it is being called in a blue screen scenario. If it is, we will check the first parameter of RCX that was passed to KEBugcheckX. Remember, because KEBugcheck2 is called the KEBugcheckX. If that is equal to 0x109, which is a crash dump code that PatchGuard uses, then we'll simply steal execution and stop it forever. Otherwise, if either of those cases fail, we will simply jump to our own driver implemented memset intrinsic, and then we'll simply return to the external code. So we do the operation that was wanted. And just as the slides say, you're probably thinking this isn't even a great attack because it's a super simple function. Like I said, memset is so primitive. It's used by almost all C code, all threads running on the system. You're probably thinking that it can't really stop an entire operating system from running, right? Well, yeah, that's what I also thought until I figured out how to actually do it, because attacking memset isn't the real problem at hand. It's figuring out how to attack memset. So my attack will simply use memset to hook execution, like I just said. However, there's a problem with that. It's being called so many times every second. So because it's so easy to understand and use, it's used all the time, like I just said. Like how many times probably a second? It's actually probably being called millions or billions of times a second, and that is a lot. Now, as fast as computers are today, you know how fast they are. So interswapping code bytes to simply hook a function, you may think that could be fast enough, and sure, it can be. You can write two threads that are completely racing against each other and attempt to patch them, and most of the time it will work, but not with this function. It is being called by every single thread on the system, probably billions of times a second. And that is a major obstacle that we have to get over. Because, like the diagram shows, if you can see, if you try to write directly memset, you're just going to jam everything up and you have a locked up system with nowhere to go. So if only there was a way we could catch execution, right? Well, there actually is. CPU debug registers to the rescue. Now, when I found out about CPU debug registers, I almost forgot that I could have used them for this purpose, but they're extremely helpful for us because we can actually use them to steal execution of a thread at any point in memory. So what happens? When you do use CPU debug registers, you're actually just going to raise interrupt vector number 1 when something is either read, written, or executed, depending on the flags you specify. Is this abusable? It seems like it's abusable to me. So how do we abuse it? Should be pretty simple, right? We can write a function to hook the interrupt descriptor table, and then that function will hijack the current handler for vector 1 and point it to our own handler. Then since every CPU has its own interrupt descriptor table, we'll call that function to hook the table on all of the processors. After we do that, all we'll need is another function to initialize the debug registers, because every CPU has its own debug registers. And then we will call that initialization function on all processors. A super simple thing, but CPU debug registers are actually very helpful to us. So how do we do this? Well, it is pretty simple, actually. Let's just start looking at the code. The first thing we have is a function, as you can see, which is called RO_initDr. It's very simple. It follows a prototype used for IPI calls. Now, what are IPI calls? They are called interprocessor interrupt calls, and they're basically calls which execute on all CPUs at the same time. That is what I will be using to call these functions on all CPUs. So our IPI call over here will simply write to debug register 7, and it will say, hey, I want to break on execution, and the size of my breakpoint will be 0. Because you need to specify a size 0 execution breakpoint. After that, it'll simply write to debug register 0 because I told DR7, all right, look, the breakpoint I want is going to be in DR0. So it'll write to DR0 the target address. Now, what is our target address? It will simply be memset. Now, we need a function, right, to actually hook the interrupt descriptor table because all our stuff won't work if we don't hook the current interrupt descriptor table. How do we do that? Well, there comes the second function, as it says on the screen. It's pretty simple. As you can see, one of the first lines is just to save the current interrupt descriptor table in a structure. After that, we'll simply take its base and add 16 times 1, or just 16 to it, because we have the first selector in it. And after that, we're simply going to flip the write protect bit. Now, why are we flipping the write protect bit? You may have thought that it's not good practice to do that in kernel code, especially if you want to read or write to read-only memory. Well, here's why we can do it. We're going to be calling this function at IPI level. And if you don't want to switch between processors and lose your current control register 0, you need to be at least dispatch level. However, dispatch level is 2. IPI is way above 2, so we are fine. We can safely switch the write protect bit, and now we can write to read-only memory. After we switch that bit, it's pretty simple. All we do is just save the current entry because we're going to need it later. So that's what we do. I'll save it as return value right there. I simply parse the data table entry. And after that, I'll take the first parameter, pass to this function called new ISR, and that will take our IDT table and it will edit it according to the low, middle, high offsets, right? And then it will simply set that to the current entry. And in the end, we're just going to set the write protect bit again in case anyone else goes snooping and then they say, hey, the write protect bit got flipped, maybe someone changed it. We don't want that to happen. So we're just going to set it back. And then after that, we're simply going to return the original entry. So this function will hook the entry it's given and return the original entry. Pretty straightforward. All right, so we have a few functions. We have ones that will actually hook the IDT. We have ones that will initialize the debug registers, but now we need to actually create the servicing routine. Now, this is what's being called when our interrupt 1 is raised, because we have hooked our IDT, we set the debug register, so this is what's called. There's a few problems with this. Well, not problems, there's a few things you need to be careful of. It is being called so many times because we are hooking such a primitive function. It's hard to emphasize how many times it's being called, but it's being called billions of times. And not just that, it's being called on all different CPUs, in all different IRQLs or hardware interrupt priority levels. So there's a lot of things we need to manage here because even on your simple computer, you probably have 4 cores. So you need to be able to manage the different IRQLs of the different CPUs on your computer. Now, how do we do that? Well, there is no easy way to do it. All we have to do is write our ISR with extreme caution. And in the meanwhile, we will have our simple driver in the background checking if our ISR is complete, if our ISR has successfully completed the patching process. So how exactly do we do that? Should be pretty simple. So this may look intimidating at first, but it is really not. So let's dig into what this is actually doing. Let's start all the way on the left. So if we're writing an interrupt service routine, right, you can't write it in plain C code, at least with the default MSVC installation. So how are we going to do this? Well, all I have is some simple MASM assembly. I'll just save some registers that need to be saved during an interrupt service routine. And then after that, I'll simply set up a stack and call the real function where I'll write my C code, which is that line that says call RLP debug trapper fall. After we call that, we will simply restore the stack by adding 28 hex to it, popping off all the saved registers, and we're done. We can return from the interrupt. So this is basically a stub, which will go on to our actual interrupt handler. Now, the actual interrupt handler is kind of tricky, but let's dissect it piece by piece. What does this do? Well, the first thing you can see is we have 2 static variables. And these are static because we don't want their value to change no matter when the function is called. So they're basically globals, right? But they're only visible to the current function. And after that, we'll set up the current IRQL and the old IRQL if we've changed it. So the first thing we're going to want to do is we have to set up a block of code, which is actually responsible for changing the code on memset, right? Because you can't let all of those things clash at the same time because that defeats the purpose of setting up this complicated hooking mechanism. So it's a very simple primitive locking thing I came up with. It's just two booleans, is patching and is patched. Both of them are false, meaning nothing has been patched yet and nothing is being patched. So how is this supposed to work? It's pretty simple. If nothing is being patched or if nothing has been patched, let's enter. And the first thing we're going to do is interlock exchange the is patching to true because we are in the process of patching. And I'm doing it as an interlock operation because so many threads are accessing this. You don't want anything to clash, so it's atomic. After that, we're just going to get the current IRQL and then check if it's equal to dispatch level or not. If it's less than dispatch level, we're simply going to raise it to dispatch level and save the old IRQL, which is what we did. Now, since we're at least dispatch level or higher, we can safely flip the write protect bit again. And now that we flip the write protect bit, we can write to read-only pages in memory. After that, the first thing we do is just write our move instruction. So this assembly, you can see where it says dereference p short, gp memset. All that is it writes two opcodes. It will move an absolute value into the accumulator register. And after that, it'll actually move the linear address of our reroute routine, which is what I'll go over next. And after it moves the linear address of our reroute routine, it will simply write jump to the whatever's in the accumulator register, which is what 0xe0ff means. Or if you're reading a Little Indian, it's FFE0. After we do that, we just got to clean up. So we set the write protect bit again. And after we set the write protect bit, if the IRQL that we came in is was not dispatch level or higher, we will simply lower back to our original IRQL. So if we were either like 0 or 1, so if you're passive level or APC level, we will simply go back to whatever the original IRQL is. Then we set is patched to true. Now that we have both Booleans set is patched to true, we will simply change out is patching to false. So because we're not patching anymore, we have patched. And the reason why is patched is true is not interlock, because if you read our if statement, is patching will always be parts first, because that's how C will read things. I mean, is patching will be parts first, is patched will not, because the second that check fails, it'll go on. All right, so underneath that, we have a simple while is patching. Now, what does that do? It basically does what you think it does. If something is patching, right, you don't want to continue execution stuff. You just want to stop the CPU while it is patching. So we're basically going to spin right there. And then the second we set is patching is still false, we will continue execution. So everything from that point will just flood down. Everything from the top, which is patching and is patched, will also flood down. All right, so we got the hard part out of the way. Now, how do we clean up? It's pretty simple. All we do is write to DR7, the 7th debug register, some flags. And after that, I'm going to write to the current DR0, the value of 0. And after that, we will simply clear a few bits in debug register 6. And I have an array that I'm using, which will basically say which processor have been patched used by my main driver. I'll simply set the current processor number to 2. Now, you're probably wondering, why are we setting DR0 to 0? Well, if you remember, the interrupt routine handler will be called on each CPU that fires the interrupt. And it'll be very complicated to try to patch your interrupt routine handler again. So we'll simply clear it here. So by the time everything's done, you will have unhooked your interrupt handler. Pretty simple. And this is some easy stuff that you can write before actually doing it. All I'll do here is you can see I'm allocating the memory pool to hold the Boolean array. After that, I'm simply zeroing it out. Then you can see I use KEIPI generic call to hook the IDT on all CPUs, initialize the debug registers. And the second that call returns, it'll start hammering the interrupt service routine we wrote. And you can see in the background, it's a simple for loop, which is constantly checking if all CPUs are finished. If they are, we'll simply clean up. We'll hook the table again, but instead of hooking it with our custom, we'll restore the original. We're technically restoring the hook. And after that, we simply free the array we allocated, and we're done. We've used debug-based hooking to hook memset. All right, so now that we've actually done that, we need to actually create the hook because we've written a jump to our hook, right? Now, what is the hook? It should be pretty simple. All we need to do is just check the current return address that is on the stack, right? And make sure that the caller of the previous caller is actually KE bug check 2. Now, how do we do that? Well, all I'm doing is checking if the current return address is KE bug check 2. And by doing that, I just check if the base is within bounds of the call to memset, KE bug check 2. Now after that, we need to check so we know that it is calling KEBugcheck2, but we need to check if this is a patchguard call, right? So all I'll do is extract that context, which is stored in the KPRCB back in KEBugcheckX, and I'll check if the RCX parameter was 0x109. If it is, well, we will go to our stall routine to stop execution forever. If it's not, we will go to memset. Easy, because we don't want to touch anything else. And so this will be written in period set. And the stall routine is where stuff starts to get easy again. All we have to do here is stop execution of the current thread forever, and then undo all the changes that our previous bug check functions have done, which means re-enabling interrupts, changing the RQL back to passive level, decrementing KI hardware trigger, and optionally writing a log file entry. I chose to do it because I want to see what happens, and then stopping execution forever. So this is pretty straightforward. We don't need much ASM, and it's a very small amount of code. So what is that code? It's basically this. So you can see the first thing we do is just enable our interrupts, lower the passive level, and then decrement the KI hardware trigger. Now the bulk of the code in the middle, it's the stuff that I put in just because I want to generate a log file entry so I can see the log file to gather some information. All it'll do is tell me where the bug check occurred, what process it occurred in, and what thread it occurred in. After that, it'll simply write it to a file and flush the file buffer so it'll be on the disk. And in the end, that last line is what actually halts execution thread. We will simply wait for the current object, the current thread object to be signaled. And since we're waiting for ourselves, we're technically just going to wait forever till we stop execution. Pretty simple. However, there's one more thing we need to do, right? Because none of this will work if we don't know the address of many functions like KI hardware trigger, KEBugcheck2, and NT memset. And the offset of the context structure in the KPRCB. How do we do that? Well, we don't have to use symbols or anything. It's already in the compiled kernel for us. All we do is start scanning KEBugcheckX. You can see the first thing I do is just scan backwards because the last call it makes is to KEBugcheck2. So bam, we found the last call. Okay, that's our address of KEBugcheck2. And right before that, there will be a lock instruction. The only lock instruction in the entire function is the one that uses KI hardware trigger. So I check for F0, which is the lock prefix, and then I found KI hardware trigger. So I'll just parse the machine code there and extract a point and generate a pointer, KI hardware trigger. Now after that, I need to find the offset of the context in the KPRCB because these are all internal values used by operating systems, so they can change at any time, right? So the KPRCB is used early in the function. So this time I'll start scanning inside KEBugcheckX from the start. And the first call in KEBugcheckX is to save the context in the KPRCB. So if I find the first call in the start, you can see right there, all I'll do is simply parse our data structures to extract the address of the context. And at the end, it's some simple API calls. I'll get the number of processors we need. And I'll use get system routine address to get an address, to get the address of memset. I can't simply use memset because remember, if I just use memset like in standard C code, that will be pointed to my driver's own intrinsic of memset. I don't want that. I want the kernel version. So I have to explicitly call it using the get system routine address function. All right, so this is all great and all, but does it actually work? Well, yeah, it should work. Let's go over a quick demo. Demo will be super simple. All it'll do is it'll do the attack and it'll be printing some stuff out to debug view. And in the end, instead of simply returning success, I will actually call KEBugcheckX with the parameter 1 to 0x109 to simulate as if patchguard is actually calling it. And because that will happen, our driver entry will never return, and our start request will never return either, because we're going to hang execution forever. So how do we do that? Well, let's just look at a really quick example right here. So I have a virtual machine right here, and right now I have unpaused it. And what this will do is it will simply call our handler. Let's get started. The first thing we should do is open up debug view because you guys should be able to see the debugger output. And I've already set up some filters so you don't see all the other system verbose messages here. So you will only see what our driver does. The first thing I will do is cd into my downloads folder. Now to load my driver, I'm going to be using a well-known Windows exploit called DSE fix. And what it does is it uses a vulnerable VirtualBox driver to overwrite a global variable called CI options in the code integrity module. And this will allow me to load my driver because it's unsigned, because I don't have an EV signing certificate, as there are a couple thousands of dollars. So I'll use this just to load my unsigned driver for now. So I use DSE fix, and you can see right here that it has modified the CI options value right now. So now I can load my unsigned driver. So I will simply start the service because it's a service. And I've just named it. Whoops. Right there. All right, bam. And you can see right here, so I just named it Supernatural because that's the name of the attack I gave it. And you can see anything prefix or SN is our attack. So you can see the first thing it did was it got called, it gathered information. So it got where KI bug check 2, the hardware trigger, memset, field offset of the context is, and the number of processors this VM has. After that, it just did some stuff, created our Boolean array, hooked the IDT, and this is the address of the original ISR that the Windows kernel has. And you can see right here, it initialized the debug registers, and bam, right after it, it has finished patching completely. Then it simply restored the hook, and right now called KEBugCheckX to simulate PatchGuard. And you can see right now this command hasn't returned yet, right? That's because it stalled execution forever, and it's called KEBugCheckX. And in fact, we can look at the log file right here. Block bug check from thread 112 in process 4, which is the kernel. So in fact, what we can do is we can go and look at the stack trace of thread 112. And 112 is obviously a worker thread because drivers are loaded using worker threads. And you can see right here, it calls the driver entry, and this is our driver. And our driver calls KEBugCheckX, right? KEBugCheck2, bam, our driver has intercepted the call and stopped execution forever, basically suppressing the PatchGuard response from ever happening again. So this is the proof of concept. And like I just said, this is the output, and our IDT will have been restored. So you don't have to worry about PatchGuard detecting the IDT again because it has been restored already. So that is the quick demo. All right, so what are some problems and improvements with this? Well, that's because, well, one of the problems and improvements are PatchGuard DPCs. DPCs are not supposed to hang, such as one of the DPCs listed there. If you do hang a DPC, you will crash with this bug check code. So I need to figure out a way to get around that. Possible things are to hook KE insert to DPC, or to block some of these calls. The FSRTL MDL recomplete devx call is actually what I think is the main PatchGuard verification routine. I analyzed some crash dumps, and it seemed that it called that. So I think that's what the main function that actually does all the stuff is. And these custom recurse routines seem to call that function. So if there's a way to get around that, that could possibly help us in suppressing PatchGuard DPC. Okay, so what do we do now with this information? All right, it's not good if we just go around, start abusing this. So first thing I did, even before I started to talk to RSA about this, was I tried to tell MS, hey, look, you have this problem. What did they do? Nothing, really. They really didn't do anything. I contacted them multiple times. They just didn't get back to me. So we'll leave it at that. Microsoft didn't really do anything when I attempted to tell them about it. So what can we take away from this? Well, system administrators can compromise an entire system, as you saw, and group separation is simply not sufficient because since you're modifying the kernel, you can get around all the security features. And of course, since this is at kernel level, it is quiet and undetected. You cannot detect this happening unless you have some special software which should be able to detect read and writes, but I don't think that exists. But what's the bigger thing we should get away from this? Well, in the next 3 months, 6 months, and the next year, there are a few things that should happen. Obviously, this needs to be patched, right? So KPP needs an update, and organizations should start to increase their hardware-based testings. Now, notice how we didn't hook a function by simply using 3 lines of code like most people would. We had to set up a complicated interrupt descriptor table hooking, synchronization, locking mechanism to hook things based on a per CPU basis and automatically undo itself. This is where its hardware-based testing should be brought in because we successfully did abuse CPU debug registers, etc. In the next 6 months, organizations should start to use these hardware-based testing things for detections of like rootkits and data integrity, just like PatchGuard has done, because 3 months is too little time. So you should start to invest in around 6 months from now in hardware-based testing at low-level firmware-based APIs and such. And in the next year, this should have this hardware-based testing, hardening, etc., should be spread to the cloud. Well, why the cloud? Well, we know where the future is going, right? Everything is running in the cloud nowadays. Everything you hear of is running in the cloud, right? So for the future of cloud security, and security for everyone, secure systems are crucial because that's where all of our data will live, like it or not, in the future. So if someone can do this in the cloud level, it's really not a good idea to not invest in hardware-based testing in the cloud because cloud systems are crucial to our future. And with that, we should be done. I will take my time now to answer questions, and I'd like to thank everybody for watching.